Hello, let's talk about sampling distributions for sample means. All right, so back in section 5.3, we talked about how you could take a population and you could take a sample, and from that sample you could calculate the average. So for example, you select the number 3 and you select the number 5 and the average is 4. We're going to put a dot on 4. So a sampling distribution for a sample mean is when we would take all possible samples of a certain size, calculate the sample mean, and then plot the distribution of all those sample means. And we noticed that a couple of things happened. Okay, so first off, when we had this population that was approximately normal, no matter what the sample size was, 2, 5, 10, 25, all of those sample means, they also looked approximately normal. We noticed that the mean of the sampling distribution, the mean of all the sample means, was the same as the mean of the population. And it appeared that as the sample size got bigger, that the standard deviation of this got smaller. And that's not always true. So this population was skewed to the right. And when we took multiple samples of size 2, we still ended up with a sampling distribution that was skewed to the right. And we could still see that right skew even until that like n equals 10 size there. And even by the time we get to 25, I still feel like I'm seeing a little bit of right skew on that. So it is becoming, as the sample size is increasing, the mean of the samples, their sample means there, it's still the same as the mean of the population. So that's still true. And we can see that the sampling distribution's standard deviation is getting smaller, but the shape is going from a non-normal shape. And as the sample size increases, the sampling distribution is becoming more and more approximately normal looking. Right? Here was another one that was bimodal. And again, we had some weird little sample shapes happening here with this sampling distribution. So when n equals 2, we got something that was just very strange. And then n equals 5, it's starting to look a little better. N equals 10 looks a little better. And by the time we get to 25, we can see that that sample size, we are getting something that looks approximately normal. Same thing again as before. The mean is the same all the way down, and it's the same as the mean of the population, but the standard deviation does tend to be decreasing. All right, so here's what we know. If we're talking about sampling distributions for means, meaning I'm talking about numerical data, I take a sample, I calculate the mean, I put a dot. I take a sample, I calculate the mean, I put a dot. A couple things I noticed. First off, as n increases, okay, and just generally no matter what the size of n is, the center of the sampling distribution is the same as the mean of the population. So in other words, the mean of all those x bar values, the on average, all your sample averages, should equal the true population average. The mean of all the x bars is the same as the mean of the population. The other thing we notice is so again, don't forget that means that it's unbiased then. Okay, so sample means do a good job of predicting the true population mean. As n increases, the spread, which is the standard deviation, decreases. So the larger the sample size, the smaller the standard deviation of the sampling distribution, which is good because remember, we're trying to hit that bullseye of the truth. So the smaller our standard deviation is, the more accurate we are in general. And then we notice that the shape looks more and more approximately normal for the larger the sample size is. So it may start off looking non-normal, but by the time we get a big enough sample size, we've got something that's approximately normal. All right, so just to reiterate, it doesn't really matter what our population looks like. The mean of the population will be the same as the mean of all those x bars. Okay, so it is unbiased. On average, we should be getting that the average of our averages is the same as the true average. Okay, now, so as we're talking about shape, we notice two things happening. Okay, the first is that for a numerical variable, something that you would take the average of, when the population distribution is approximately normal, the sampling distribution can also be modeled with a normal distribution. So if your parent population is approximately normal, your sampling distribution of sample means is going to be approximately normal for any sample size. So I can take a really small sample from a normal distribution population and I can end up with a approximately normal sampling distribution. Okay. I also noticed that when the population is non-normal, it takes a while for me to get to something that looks approximately normal. So in section 5.3, we talked about the central limit theorem, or CLT, and it states that when the sample size is sufficiently large, the sampling distribution of the mean of a random variable will be approximately normally distributed. We also need for the sample values to be independent of each other and for n to be sufficiently large, that when you take one sample, or when you take the samples, that they're independent of each other. So how large is sufficiently large? Like for the bimodal population, we got this trimodal thing, and then this thing that was kind of symmetric but not normal. And by the time we were getting to 10 and 25, it seemed good enough. But for the right skewed one, it didn't seem like 10 was big enough. I had to keep going. All right, so what we're going to do is we're going to draw the line in the sand, okay? And just like with proportions, where we were checking that n times p and n times 1 minus p are greater than 10, for a sampling distribution for a mean, we would like our sample size to be at least 30. Okay, so from the rubric here, it says for a numerical variable, if the population cannot be modeled with a normal distribution, the sampling distribution can be modeled by an approximately normal distribution, provided that the sample size is large enough, that is greater than or equal to 30. So by the central limit theorem, if your population is non-normal or it's unknown, as long as n is greater than or equal to 30, your sampling distribution, that's a really good line to draw. It's going to be approximately normal. Be very careful with this rule. This rule only applies to means. It only applies to numerical variables. So if you're checking for a proportion, you still have to check the n times p and the n times 1 minus p. Just because your sample size is bigger than 30 is not going to necessarily satisfy this same condition for proportions. The central limit theorem only applies to means. Okay? Now you need to be careful when you're talking about where you are on your formula sheet. We want to look today for where on the formula sheet it says random variable for one population x bar. Okay, so we're looking for a sample mean today. And we've already said this, but the mean, which is going to be our center, is the same as the mean of the population. When I'm talking about standard deviation, the standard deviation, the reason why it decreases as the sample size increases is because the standard deviation of x bar is what you get when you take the standard deviation of the population divided by that square root of n. Now again, this formula really only works if we're either sampling with replacement or if we've got less than 10% of the population. So that 10% condition still applies. Okay, so I have this multiple choice question here. It says, a large population has a mean mu and a standard deviation sigma. A random sample of size n will be taken from the population. The central limit theorem tells us that, okay, now I went ahead and put the central limit theorem up real quick. Let's reread that. The central limit theorem, CLT, states that when the sample size is sufficiently large, the sampling distribution of the mean of a random variable will be approximately normally distributed. Okay, so the central limit theorem says that for large sample sizes, the sampling distribution of all those x bar values will be approximately normal. Okay? All right, so the first answer choice here says the mean of the sampling distribution of the sample mean is mu. All right, now that is true. That is a fact. Truth. Check mark. But that's not what the central limit theorem says. Okay, so we're going to have to be really careful on these answer choices. Some of them may be true, but it's not asking us which statements are true. It's asking us, what does the central limit theorem tell us? Okay, the standard deviation of the sampling distribution of the sample mean is sigma over the square root of n. Okay, that's also true, but that's also not what that central limit theorem says. Okay, if n is large, the sampling distribution of the sample mean is approximately normal. That's true, and that is what the central limit theorem tells us. Okay, the next one says, since the population is large, the sampling distribution of the sample mean must be approximately normal. Okay, this is not true. The population can be enormous, but it's that sample size, not the population size, that determines whether or not the central limit theorem can be applied in this situation. The standard deviation of the sampling distribution of the sample mean is greater than the standard deviation of the population. That's false. It's going to be less than, because if you take sigma and divide it by the square root of n, that's always going to be less than whatever sigma is. But also, that's not what the central limit theorem says either. Okay, so we want to be careful with central limit theorem. It is a statement that talks about if you have a large sample size, your sampling distribution will be approximately normal no matter what your original population looks like. But it's also only good for sample means, not sample proportions. So you got to be careful. All right, so answer choice here, C. Or here's another problem. It says the length of human pregnancies from conception to birth varies according to a distribution that is approximately normal with a mean of 266 days and a standard deviation of 16 days. I have a question that says, find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. All right, so here's what I know. I know that this variable is numerical because we are measuring the length of pregnancy in days. So from now on, when you're reading the problems, if you identify you're dealing with a numerical variable, you are almost certainly in a means problem, because if numerical data, we usually take the average of. The population here is all human pregnancies. Okay, and so it's asking us, what's the probability, if X is the length of pregnancy, that a woman has a pregnancy that lasts for more than 270 days? So one woman, one X value greater than 270. All right, so what do I know? According to the problem, it's approximately normally distributed. It has a mean of 266 and a standard deviation of 16. I want the variable X is days and 270. So this is like sections, the first section of chapter 5.1 and 5.2 here. All right, so I'm going to go ahead and use my calculator, okay? I'm going to normal CDF, okay? And I'm not going to pull my calculator out on this video, but if you need help with that, just send me an email and I'll try to help you out. So norm CDF, 270 up to infinity, mean of 266, standard deviation of 16, and I get 0.40, which is going to be my probability, 0.401. Okay, so about a 40% chance that a single woman has a 270-day or longer pregnancy. Okay, now suppose we choose a simple random sample of 6 pregnant women. Let X bar be the mean pregnancy length for the sample. What is the mean of the sampling distribution for X bar? All right, so for my formula sheet, I know that the mean of X bar is the same as the mean of the population. And since the mean of the population was 266 days, the mean of the sampling distribution should be 266 days. Okay. it says calculate and interpret the standard deviation of the sampling distribution of X bar. All right, so again, my standard deviation, in order to use that formula, I've got to make sure that I'm less than 10% of my population. So is 6 less than 10% of all human pregnancies? Yes. For sure. Okay. And so standard deviation of X bar is sigma over the square root of n. That's going to be 16 over the square root of 6, which is about 6.53 days. 6.53 days. Now, I've got that little step boxed in with the radical. It is incredibly important that you always show your fraction setup. The 16 divided by the square root of 6, where you substitute into that equation. When you go to plug these into your calculator, use 3 or 4 decimal places over here, and that's totally fine. But you're going to want that radical there in your work, because they're going to want to see that on the AP exam, that you know how to use this formula. Okay. All right, so find the probability that the mean pregnancy length for 6 women in the sample exceeds 270 days. Now, on first glance, this sounds like that other question, right? What's probably X is 270, but it's not 1X. It's the mean of the sample of 6. So we're not talking about an X being greater than 270. We're talking about an X bar being greater than 270. All right, so what do I know? I know the mean, and I know the standard deviation. And I also know that it's stated that the population is approximately normal. So that means that my sampling distribution is also approximately normal. So I have an approximately normal distribution with a mean and a standard deviation. All right, so I'm going to go ahead and label this normal distribution, mean of 266. And I wrote that up there as 16 over the square root of 6 for the standard deviation, but you could also write like 6.531 or something like that. Okay, I've got my 270 exceeds to the right. I'm going to use my norm CDF, this time from 270 up to infinity, with a mean of 266 and a standard deviation of, and in my calculator, I typed in 6.532, I think, when I typed this in. instead of the radical, and I got about 0.270. So that's my probability. Now, just so we're clear, it's a coincidence here that the probability is 270 and the weight is 270. That's just super cool, but it has coincidence in this case. All right. So one thing I want you to notice that the probability that the average was less than 270 I guess I wrote these backwards, exceeds 270, sorry, was 27%, but the probability of 1 was 40%. So it's far more unusual to have an average of 6 women that are 4 days overdue than just one woman being 4 days overdue. A lot of times you're going to find that when you take the probability in a sampling distribution, that you're going to get a far smaller probability than if you were to have calculated that single value. Or another way to think about this, let's say you're walking down the hallway and you see one really tall person, like say 7 feet tall. If you see one really tall person, that might catch your attention, like, oh wow, that person's really tall. But if you saw 6 really tall people walking together down the hallway, that is really going to catch your attention. Like, wow, do we have a basketball team here or something like that? So that's going to catch your attention. One single high value or one single low value in a sample is far less unusual than having an average of a set of very high or very low. Because if that 7-foot person gets stuck in a sample of just regular size people, the average number is going to be far less than 7 feet. In order to get an average of 6 guys being 7 or 6 people being over 7 feet tall, we're going to have a lot of really tall people, and that's going to be an unusual sample. Okay, all right, next question. Keith is the manager of an auto care center. Based on service records of 3,500 customers from the past year, the time in minutes that a technician requires to complete a standard oil change and inspection follows a right-skewed distribution with a mean of 30 minutes and a standard deviation of 20 minutes. For a promotion, Keith randomly selects 40 current customers and offers them a free oil change and inspection if they redeem the offer during the next month. All right, so the question says, can we determine the probability that a single oil change will exceed 35 minutes? Why or why not? All right, so I know that my variable is numerical because X is going to be the time to complete an oil change in minutes. My population are those 3,500 customers, and the shape of the population is stated as skewed right. So we want to know, can we find the probability that X is greater than or equal to 35? In this case, no. The population is not approximately normal. So we don't have the ability to calculate the probability that the time is bigger than 35 minutes given the current information. It is possible that if we actually had all the service records in front of us, we could go through each and every one of them and count the number out of 3,500 that were greater than 35 and do it that way. But we're not provided that information. So I'm unable to calculate this probability of an oil change exceeding 35 minutes here because I don't have enough information. Okay, it's not normal, and so I can't use normal CDF, so not possible here. Okay, what about the sampling distribution though? So what would the sampling distribution of X bar look like? Describe it for 40 randomly selected customers. So remember, when we talk about sampling distributions, we would talk about shape, center, and spread. So let's start with shape. The sample size is 40, so the sample size is large enough. 40 is definitely greater than that threshold of 30. So by the central limit theorem, the sampling distribution is approximately normal. So even though our population is skewed to the right, we've taken a large enough sample that the sampling distribution will be approximately normal. The center, the mean of X bar is supposed to be the mean of the population. That's supposed to be 30 minutes, so that's going to be the mean of our sampling distribution as well. And then the spread, the standard deviation should be sigma over the square root of n. That's 20 minutes divided by the square root of 40, which is about 3.16 minutes. And just to confirm, I checked, is 40 less than or equal to 10% of our population? Now, in this case, we know the size of the population. It's 3,500. And 10% of 3,500 is 350. So I can say, for sure, absolutely less than 10%. I don't need to do like a, well, in theory, it's reasonable that, I don't have to do that this time. I can actually check. All right. Now, Keith budgets an average of 35 minutes per customer for a technician to complete the work. Will this be enough? So calculate the probability that the average time that it takes to complete the work exceeds 35 minutes. So I know I can't calculate the time that one customer will exceed 35 minutes, but could I do an average, a mean time greater than 35 minutes? All right, so I know from the previous work on the problem that this is normally distributed because the sample size was large enough. I know that the mean was 30, and I know the standard deviation was 20 over the square root of 40, and which is about 3.16. And I don't know why that decided to center on there instead of being right underneath that. And I want to know what's the average is greater than 35. So I'm going to use my norm CDF from 35 up to infinity with a mean of 30 and a standard deviation of about 3.16. Gives me 0.056923. That is about 0.057 for that probability. Okay. All right. How much time per customer should Keith budget if he wants to be 99% certain that he doesn't go over budget? All right, so what this is basically saying is he wants 99% of the jobs to be less than the budget time. Okay, we want average. We want 99% of the average possibilities here to be less than that budget time. All right, so we're still talking about average time. On average, how long should it be to make sure that 99% of possible average times are less than whatever that is? We don't want to go over budget. So we know the mean is 30, standard deviation is about 3.16. I want something 99% at or below. How much time should we budget for the average? Okay, so remember, if you want to work backwards, we're going to use inverse normal. I know I want 99% to the left. The mean is 30, standard deviation is 3.16. That gives me about 37.35. So he should budget about 37.5 minutes, basically, for this. So if he budgets 35 is what it was. And the last problem said he budgets 35 minutes per customer. That is not going to be enough to keep 99% of the averages under time. So he probably needs to boost that up a little bit more on his schedule. Okay. All right. Last question. For every household in a particular county, the total water use in thousands of gallons over the course of a year was recorded. The mean water use for the households in the county was found to be 162 with a standard deviation of 140. Based on the information above, could the distribution of household water use for that county be approximately normal? Okay, so just so we're clear, we're not talking about the sampling distribution here. We're talking about the actual population. Based on this above, could the actual population be approximately normal? All right, so here's what I know. If this is normally distributed, 99.7%, almost all of it, has to be within 3 standard deviations. So I'm going to start off kind of sketching that. The mean is 162. The standard deviation is 140. So if I'm talking about within 3 standard deviations, so let's say I start at 162 and I go down 1 standard deviation, that puts me at 22. When I go down 2 standard deviations, I get to negative 118 gallons. All right, so the smallest number of gallons that could be used is 0. So we've basically run out of room for this to be approximately normal. I can't say that this is approximately normal because I can't fit 3 standard deviations in logically. Okay, so no, this can't be an approximately normal distribution because 99.7% of water use needs to be within 3 standard deviations of the mean, and 0 gallons, which is our lowest logical value, is less than 2 standard deviations below the mean. So our curve can't possibly extend enough for that approximately normal distribution. If I had to take a guess, I would guess that this is skewed to the right. Okay, so a random sample of 50 households will be selected and the mean water use calculated for the households in the sample. Is the sampling distribution for the sample mean of random sizes, samples of size 50 approximately normal? So I know that the population is not normal, but could the sampling distribution be approximately normal? So I know that by central limit theorem, that as long as the sample size is sufficiently large, in this case 50, and 50 is greater than 30, so we're good to go there, the sampling distribution is approximately normal. So yeah, even though the population is non-normal, the sample size is large enough, greater than or equal to 30, so that the sampling distribution of x bar is still approximately normal. And you see how I did this check of the 50 greater than or equal to 30? Okay, you need to show that check. Yes, the sample size of 50 is greater than or equal to 30, check mark, to show that you actually verify that you know what you're talking about. All right, so suppose that the annual indoor water use, so different data value here, for the same county is approximately normally distributed with a mean of 57 and a standard deviation of 12. If a random sample of 50 households is selected, what is the probability that their mean indoor water use in thousands of gallons will be greater than 59? All right, so notice that it's asking us for the probability of a mean. What do I know? I know that the population of the indoor gallon use is approximately normal because it was stated, with a mean of 57 and a standard deviation of 12. I know that I'm going to take a sample size of 50, and I want to know, is that going to be good enough for the X bar value to be greater than or equal to 59? Okay, so first off, the sample size is large enough, 50 is greater than or equal to 30, so I know that the sampling distribution is approximately normal. I could also say here that the population was approximately normal, which means my sampling distribution is approximately normal. Either of those would be good enough for shape. I know that the mean of X bar needs to be equal to the mean of the population, which in this case was given as 57. I know that 50 needs to be less than 10% of all the households, and that's reasonable. That's like 500 or more households in a community. I'm sure that's fine, which is reasonable. So I can use my standard deviation formula, sigma over the square root of n. That's 12 over the square root of 50, that sample size, which gives me a standard deviation of 1.697. All right. So what do I know? What's the probability that X bar is greater than or equal to 59? I can draw my picture. There's the X bar on the axis. Okay, 59 is the boundary, shaded to the right for greater than. I know the mean is 57. Standard deviation is 1.69706. Norm CDF from 59 up to infinity. And I end up with a probability of 0.119. Okay. All right, so just to recap here. I know that if I'm talking about repeatedly taking samples from the population and calculating the mean of those samples, that if my population is approximately normal, the shape of the sampling distribution for the X bars is approximately normal for all values of n. It doesn't matter how big the sample is. I know that if my population shape is unknown, I don't know what it is, or if it's non-normal, the shape of the sampling distribution is also going to be approximately normal, as long as n is at least 30. That's called the central limit theorem, and it's only good for means. Only good for means. You cannot use central limit theorem for proportions. For proportions, you have to do that n p greater than 10 and n times 1 minus p greater than or equal to 10. All right, the center, which we're going to use as mean of my sampling distribution of X bar, is going to be the same as the mean of the population. Okay, the spread, that standard deviation of the sampling distribution, you're going to have to use the formula sigma over the square root of n to calculate it, and it's only accurate if you're either sampling with replacement, or if you're not sampling with replacement, you got to make sure you're less than 10% of your population. Okay, remember that your formulas are on your formula sheet for the mean of X bar and the standard deviation of X bar. You don't have to memorize those, just got to be able to use them. And that when you're doing one of these problems, if you can verify the shape is approximately normal, you can compute the mean, you can compute the standard deviation, you've got a standard normal distribution probability question. So you should be able to draw your picture, you should be able to identify the parameters, you should be able to identify the boundary and direction and use your calculator to find those probabilities. All right, so that's it for me. Good luck on today's assignment and let you know if you have any questions.